Section 3 gets into definite integrals. That's what they call them. In the past, we've worked with integrals, and now we're working with definite integrals. And you'll learn why they're called definite integrals here in a little bit. So in the last section, we were talking about area under a curve. We were talking about summations. And actually, I want to pose a question to you. Draw a graph of a velocity versus time for a car that's driving at 60 miles per hour. Give me a graph of velocity versus time for a car that's going 60 miles per hour. If I'm graphing velocity versus time, then this is velocity and this is time, right? If I'm going 60 miles per hour,
Yes, that's what I drew. I totally drew that. I'm so
Good.
excited right now. These small children live.
okay, people just rose from the dead for sure.
Yeah, they did.
Question. If this is the case, how far, and it's just like whatever comes to mind, how far has the car gone in 2 hours if it's driving like this? 120 miles. That's right. Question 2, if this is time and I'm labeling things in terms of hours, here's 1 hour, here's 2 hours, what is the area under the curve from 0 to 2? 120. Coincidence? Draw me a sketch of acceleration. If acceleration is constant at 10 meters per second squared. Let's make it, instead of meters per second squared, let's make it miles per hour per second. 10 miles per hour per second. That's pretty fast. That's a pretty good acceleration. Yeah, it's not really a jet, but it's pretty fast. What would that graph look like? Constant acceleration, 10. 10 miles per hour per second. What after, let's say after 5 seconds, what would the velocity of this thing be? After 5 seconds, it would be 50, because it's accelerating at a rate of 10 miles per hour per second. So after 5 seconds, each second that goes by, it's going 10 miles per hour faster, right? So its velocity would be 50 miles per hour. 1, 2, 3, 4, 5. What is the area under the curve from 0 to 5? 50. What is the integral of acceleration? Velocity. So if this is 10, what would the equation for velocity be? A equals 10, so V equals A of t, so V of t equals 10t. Show me that graph. What's it look like? Steep. Has a slope of 10, right? And if we're accelerating from rest, if this object had a velocity of 0, then where would that line start? 0, 0. So my line goes up like this, right? Okay. And then I'll put some units on here. Let's call this 1, 2, 3, and then therefore this would be 10 here, and then 20 here, and then 30 here. So this thing has a velocity that's changing, right? Because it's accelerating. How far has it gone in 3 seconds? I'm asking for the position, right? Position is the integral of velocity, right? So we could integrate this equation, v of t equals 10t, right? Integrate that to get position. The position function would be s of t equals 5t squared plus v naught, which was 0, so that's gone, plus the initial position. If we call the initial position 0, then that's it, right? So after 3 seconds, where are we at?
Wow.
45. So s at 3 would be 45. What is the area under this curve? 45. Okay? So what could we say? Just some sort of general conclusion from what you just learned. It's not awful. It's awesome.
The area of the region equals the integral or something.
The area under the curve from A to B tells you
The integral.
the value of the integral. Okay? So, or if you were talking about like position, tells you your position at the end of that interval. So if you're given a velocity function, you can integrate it over an interval, find the area under the curve, and know the position, the amount of distance traveled over that interval. So we'll get into more of that here in this section and beyond, but that's a really, really important connection to make. So I wanted to make that connection for you now. Okay, in the last section, we developed a way to calculate the area of a region under the curve. Why did we do that? Because of this. All right? It's like learning to crawl before you learn how to walk. You didn't know why we were doing it, but now you do. But above the x-axis and bounded on either side by vertical lines at A and B. Okay? This A and B notation here is very important. We're going to be using it for the rest of the semester. But every single thing that we did was bounded by the x-axis. We were stuck finding an area here. What we're going to do in this section is get away from that. We're not going to be bounded by the x-axis anymore. We can still find areas. They're not really areas. We can call them areas. We can use left sums or right sums, but either way the area under a curve is this guy right here. The limit as n approaches infinity, the number of rectangles goes to infinity. I add up all those rectangles. This right here represents the height, and this is the width over the interval from A to B. So the problem with this idea of area is it restricts us to regions above the x-axis because we're talking about areas, and areas are always positive. If we start talking about regions below the x-axis, we wind up finding negative results. Yeah. So geometrically speaking, we can't have a negative area. But in terms of calculus, it's extremely useful for us to be able to talk about what we're kind of calling a negative area. Okay? So it turns out that if we introduce a concept, which I will here in a second, some notation, and get over the usual idea of area, and notice I'm putting area in quotes. I'm not really saying it's an area, we're treating it like an area. Then we can open the door to a whole new level. Kinda area, yeah. So we're like crossing the threshold into something much better than what we've been trudging through. Yeah. So here's your concept. If a function is continuous on the closed interval from A to B, that's my interval, then the function is integrable on A to B. And I did not make that word up. So that's the idea, and we've been seeing that notation if a function is continuous over some interval all year long. So that should be nothing new. And it's kind of a no-brainer. If it's continuous, then I can differentiate it. If I can differentiate it, I should be able to integrate it. Here's your notation. This is what we've been looking at right here. The notation becomes a little bit simpler, a little bit more elegant when I write it like that. So we already know this symbol right here, the integral symbol. A and B are the endpoints of my interval. Notice that A and B aren't necessarily written here. Okay? So using this notation, I can now show where I'm supposed to start and where I'm supposed to stop. I still have this f, I still have this function sitting here. My function is still sitting here. There's still a delta x, the dx. Yeah. So everything is still there. It just simplifies down and makes us able to see exactly what we need to see, all in one nice, beautiful little chunk, rather than stuff being scattered all over the place. This thing right here is called the definite integral. It's an integral because we have this symbol right here for sure. But it's called a definite integral because I'm showing you the bounds over which we are going to wind up integrating. So the notation allows us to get away from these strictly positive results that we've been dealing with, which you'll see as we go along. So we learned how to evaluate integrals, but that's not what we're doing here. We're still going to go back to this guy. We're still going to evaluate this the same way that we did in section 2. So we're still using sums and limit notation. Okay? And then the important note down at the bottom, this does not mean that you can have a negative area. We just have to get over the idea that it is strictly a geometric area. We can still call it area, but it's not really, geometrically speaking, an area. So here's your big example here. Consider the function f of x equals 2x. I've shown you the graph. I want to set up the definite integral over the interval -2 to +1, and then evaluate using right endpoints. So if I look at the graph, here's -2, here's +1. If I stretch and find this area here, then I have that region and I have this region. If you find the heights of your rectangles in this region, your heights will wind up being negative. Which means when you find the area of this region will wind up being negative. The area of this region will wind up being positive. Just by looking at the graph, what will the result be? Negative. Because I add this negative area which is bigger than this negative area, smaller, and I wind up with a negative result. Okay? And what I'm trying to tell you is that's perfectly fine, as long as we don't think of it as an area, geometrically. Okay? So it is possible to do this. We just have to get over it being a negative result. There is a deeper meaning behind it. So, set up the definite integral over the interval. To do that, all I need to do is draw my integral symbol, label the lower and upper bound, so -2 and 1 from a to b. Yeah, lower and upper bound. And then my function is 2x and dx. Okay, it's that easy. So everything's labeled now. Now I'm going to convert that back over to my limit definition with sums. So I'm going to write limit as n approaches infinity of the sum from I equals 1 to n of f at c sub I delta x.
Okay, why is it just because of the notation of the integral that we write dx instead of like in the sum of that? Or does that?
Can I just say yes and you'll be happy?
Yeah.
Okay. Yes. We are starting to learn how to walk. So you're going to see some things that you might question, but trust me. So now that we're here, we're right back to where we were in section 2. Okay? The only thing that's new here in this section is this idea right here for now. So from here, I need to go back to what I was doing in section 2, which means I need to figure out my delta x. It's still b minus a, so 1 minus -2, which is 3 over n. I need to figure out my c sub I. Luckily, I specifically say right endpoints here, so there's no confusion. We're just going to use right endpoints. C sub I equals -2a, so it's a right there, and then plus I times delta x. So plus 3I over n. Now you want to do f at c sub I? Okay. F at c sub I equals 2 times negative 2 plus 3I over n. Okay? All right. So now my summation that I'm actually going to be using is the limit as n goes to infinity of the sum from I equals 1 to n of my f at c sub I, which is 2 times negative 2 plus 3I over n times delta x, which is 3 over n. Notice I did not distribute that 2 in because I know that I'm going to just pull it right back out again. I have a constant sitting here and a constant sitting here. Pull those out. So this becomes 6 over n out front, limit n approaches infinity of I equals 1 to n of negative 2 3 over n I. Convert. We still have the 6 over n sitting out front. I'm going to do the conversion here. Negative 2n. 3 over n times and we are still taking the limit as n approaches infinity. I just haven't written it down. Cancel some stuff? Now you got me saying it. N, n, n. Anything else? Maybe, but let's be safe and just write this down. So we have 6 times negative 2 plus 3 times n plus 1 over 2. 3 over n. Right? Okay. So this becomes negative 12 plus 18 over n times n plus 1 over 2. Yes. Let's reduce that. This is 1, this is 9. Plus, everybody agree? Okay, keep going. This reduces. So I get negative 12 plus 9. So negative 3 plus 9 over n. And we're still, remember, taking the limit as n approaches infinity. So therefore, the answer is negative 3 for the area under the curve.